this video we're going to talk about operational amplifiers, or op-amps for short. So op-amps are a pretty simple integrated circuit that you can go buy now. Supposedly they're anywhere from $1 to $5. The internal circuitry of an op-amp is pretty intense. There's a lot of transistors and things in there that kind of get the whole thing to work. We're just going to do a very, very simplified model, and then we're actually going to make a ton of assumptions, and then I'm going to show you 3 different examples here. We're also going to do steady-state operational amplifiers. So in this last operational amplifier, we're going to put a capacitor in there, and rather than doing the differential equations and solving for the transfer function, which is what you would potentially do in like a advanced circuits course or a controls course, we're just going to look at the impedance of the system and just look at once all the transients have died out, what does a steady state magnitude and phase look like. So let's jump into this model here. So the way a op-amp works is you draw it like this triangle, and typically when you draw it, you just draw it with a triangle with a minus and plus on it, but I've sort of exposed I would say like 2% or maybe 5% of the circuitry on the inside. So what you do is you hook up a negative voltage source and a positive voltage source, and that doesn't necessarily mean that one is negative and one's positive. It's just it's a nomenclature thing. So you could hook up 5 volts and 3 volts to here and it would be fine. But you call the high end up here negative and the bottom and the low end down here positive. Both of them are grounded, and this is actually, the way it's modeled is not actually connected to any part of the other circuitry. So this kind of acts like a voltmeter. And what you're doing is you're measuring the voltage differential between the two, which is why here you have this output voltage over here is equal to some G gain times V plus minus V minus. So you measure the voltage differential, you measure the voltage drop across this resistor, and then you amplify the voltage by some G and output that to here. You're obviously going to have some output resistance in there, but in terms of the assumptions, we're going to assume that output resistance is 0, and we're actually going to assume that the input impedance is infinite. If you remember in the last video that I posted about talking about source voltage and measuring something with a voltmeter, when you're measuring something with a voltmeter, you want the impedance to be infinite so that no current goes through it, which is what we're doing here. We're assuming infinite impedance so that no current runs through these 2 terminals, right? So this is current going this way and current going that way into the system. We're assuming that current is 0 because the input impedance is infinite, and so that's what these assumptions are saying here, that I minus and I plus are 0. And then we're also assuming that the output impedance is 0, so that whatever voltage we are outputting to the rest of the circuit is exact. There's no losses associated with that. Now, you're probably wondering, I mean, if you put in this voltage here and you get this differential, like how does it actually boost the voltage? Well, if you put in, say, 5 volts and 3 volts here and the gain is 2 or something like that, where does that extra energy come from? Well, you have to have a power supply hooked up to your op-amp. So typically, op-amps will run at like plus or minus 15 volts. So you'll have your connections here and here at the positive and negative end, but you'll have like a 15 volt power supply that actually is what boosts the output. Now keep in mind that you are going to have saturation, so if you put in something that has like a voltage of 12 and you have a gain of 2, you're not going to get 24 volts because you can't get energy from nowhere, so it'll actually saturate at 15. We're going to ignore all of that and just say that whatever output we think we're going to get, we get it, okay? And so I think I kind of touched on a lot of things. We're going to assume that the input impedance is infinite, which means the current is 0. Since the current going through it is 0, it means that the voltage drop across that resistor is also 0. I mean, voltage is current times resistance. If the current is 0, there's no voltage drop, so that means the voltage, the positive and negative end, are the same. And obviously that's not true, but we're making an assumption here. The output resistance is 0 and the gain is infinite. So if this term goes to 0, this term goes to infinity, and infinity times 0 is something, V out, right? That's just kind of how the cookie crumbles. All right, so let's do this simple non-inverting amplifier here. So I've sort of closed the hatch again and just shown the triangle with the minus and plus here. Instead of perfectly denoting V minus and V plus, I actually have the input voltage here. The left side is grounded through a pull-down resistor,
and then we have the output voltage here. We actually, in this case, we have a feedback loop here, so we have this wire with the resistor here going from this point through V out to this point, which I call point B. Okay? And so let's walk through this, how this works here real quick, okay? So by inspection, because V plus minus V minus is 0, V plus and V minus are the same. Okay, so that means that this terminal is the same as V minus. VB is the same as, V plus is the same as VI. So the positive terminal is the same as the input voltage. Point B here is the same as the minus voltage, which is from this terminology here. And since we know that V plus minus V minus is 0, it means that the minus terminal is the same as the positive terminal, which means that the voltage at point B is the same as the input voltage. So that means the input voltage, the voltage here is the same as the input voltage, and the voltage here is also the same as the input voltage. Okay? We can do a KCL, a Kirchhoff's current law at point B, and we can say all of the currents going in, so I'm going to call that I1, is equal to the sum of all the currents going out. So I have I2 and I minus. So I have I1 is equal to I minus plus I2. But we know from our assumptions that I minus is 0, which means that I1 and I2 are the same, and I just call it I. So that means we actually have a current loop here where this current is I. Okay? And since I have a current loop that is I can do a KVL now, and I can say, okay, this is a voltage increase, V naught, and then this would normally be a voltage drop, but I am going in the opposite direction of the current, which means that's a voltage boost, and so it's V naught plus IR2 plus IR1, same thing, and that equals 0 because these 2 points are ground. It's a complete loop. Technically, if I were designing this circuit, all of these points would be connected to the same ground junction. Okay? Then you do a little bit more finagling here. You can look at point B and you can say, well, I know that point B is VI, and if I go this way, right, I am going to drop down to ground. And so what I can do is I can say, okay, let's start at 0, and I'm going to go from 0 and I'm going to do a voltage drop. So that's going to be negative I1R1, and that's going to be equal to the input voltage. So that means I've solved for my current, and my current is negative VI over R1. So then what I can do is I can take equation 5 and I can solve for current, and then take equation 6 and plug that into equation 7, and I get that V naught is VI R1 plus R2 over R1. And so you can see here, this is a non-inverting because the sign, right, if you put in a positive voltage, you're going to get a positive voltage output, and it's going to be scaled by this. So you can choose R1 and R2 to either increase or, I think that's going to increase your, this is going to amplify your signal no matter what. Okay? So hopefully that sort of made sense there. I did this one in rigorous detail, and there's also at least in the textbook, there's this simple inverting version where if you look here, rather than the input voltage hooked up to the positive terminal, you have the input voltage hooked up to the negative terminal, and you basically have the same resistances. If you do the exact same equations, but you do it with this circuit, you actually find that V naught is equal to negative VI R2 over R1. And so this is a simple inverting because it means that the output voltage is going to be the opposite sign of the input voltage. And now I didn't do the math here on the whiteboard here because I wanted to leave that as an exercise for you to see if you can get the same answer. Follow the exact same steps using KVL and KCL, and make sure to plug in your assumptions, and you will hopefully get that answer there. The reason why I put this simple inverting amplifier on here is because you can actually build a first order filter using this model here. If you take the exact same circuit, but you throw a capacitor in parallel to the second resistor, what you can do is you can combine again, we're doing steady state, so if you combine the impedances of these two elements into Z2, you'll see that this circuit looks exactly like this circuit, which means that the output voltage is just equal to negative VI Z2 over Z1, where Z1 is the impedance of this resistor, and Z2 is the impedance of these two circuit components put together. So how do we get this, the impedance of this component here? Well, the impedance of the first resistor is just R1, that's easy. The impedance of the second one is a little difficult because they're in parallel, so you have to add the reciprocals of the impedances, and the impedance of a capacitor is actually equal to 1 over J 2 pi Fc, where C is the capacitance, pi is pi. F is the input frequency of, it's the frequency of the input. And so the impedance actually changes with respect to the frequency of the input. So if you remember how capacitors work, if you put in a voltage source, the voltage in the capacitor is going to ramp up. And if you remove the voltage, it's going to decay down. If you remember like RLC circuits and RC circuits, I think if you remember RC circuits are first order, and then RLC circuits, because there's that inductor in there, is second order. And you can, hopefully you've taken like an introductory circuits course where you've learned that, that RC circuit has a time constant associated with that decay, and then an RLC circuit has a frequency and damping associated with those three terms. And essentially this impedance comes from those laws that I think it's the derivative of voltage is equal to the current or something like that. I always forget. I always have to look it up. But if you do all that and you convert it into the frequency domain, if you take those derivatives and convert it into the frequency domain, you'll get the impedance as 1 over J. Again, J is the imaginary number, 2 pi Fc. So then if you plug the impedance of the resistor and the impedance of the capacitor into this equation and add everything together, you'll get this equation here for Z2, R2 over 1 plus J 2 pi Fc R2. And then you can plug Z2 into this equation up here, a negative VI Z2 over R1, and you'll get to the final equation for your inverting amplifier. Or it's a first order and it's inverting. So what you really have to do, if you want to have a first order filter that's non-inverting, you either have to you probably have to create a non-inverting amplifier like this and add a capacitor to it, or you could just tack on a inverting amplifier onto it, so it'll filter and invert it, and then you'll run it through an inverting filter again, and it'll bring it back the other way. I'm not sure how it's typically done, having not built one myself. Anyway, so you get negative VI over times R2 over R1 times 1 plus J 2 pi Fc R2. And if you look at this equation, if J is equal to 0, right, if you pop up here, and if you divide by VI, remember that output over input is equal to G, the transfer function. If you look at this equation, if J is equal to 0, right, that's when you put in a DC gain, so it's a constant voltage source, not non-oscillating, so direct current. You just get negative R2 over R1. And that's the exact same transfer function that you got with the simple inverting. So the textbook calls this G naught, which is technically like your zero frequency transfer function, or your zero frequency gain, or your DC gain G naught. And so what you can do is you can divide the whole thing by G naught and get G over G naught and compute the magnitude, and you get this equation here, which is 1 over square root of 1 plus 2 pi Fc R2 quantity squared. And if you look at this equation, if F is 0, the gain ratio is 1, and as frequency increases, you're going to lower the gain, right? You're going to filter out those high frequencies. And so you can draw a Bode plot here where you plot gain in decibels here. So this is gain in decibels. And this first order filter has a very, very, I want to say standard form here. I guess it's something you could say it's a standard form, where right at the cutoff frequency, where the cutoff frequency is 1 over 2 pi CR2, and you can get that just from inspection of the equation, you're going to get negative 3 dB. And negative 3 dB has a very, it's sort of a quantity that's typically reported in many first order filters, and it basically says that after this point, right, the slope is going to be minus 20 dB per decade, where a decade is a power of 10, Okay, so every time you increase frequency by a power of 10, you're going to go down 20 dB. The phase plot, so if you put in an input signal that has a certain phase, your output is going to lag behind by a certain amount. And you have to think that, it takes time to load up and sort of it's like filling up a bucket of water, right? It takes time for the water to fill up, and then if you open the valve and let the water come out, it's going to take time for that water to come out. And so every time you filter a signal, every time you apply some sort of signal conditioner to your signal, your output is going to lag behind. And it's really important, especially in control design, to make sure that your lag, your phase lag, is not over a certain amount. And that phase lag is, for a first order filter like this, is quantifiable. And all you need to do is compute, I don't know if you guys remember your complex variables, but if you compute the phase of the numerator minus the phase of the denominator, you can get the phase of the entire thing. And it turns out there's a if you look at the phase of this, there's a very simple equation. It's negative tan inverse of frequency over cutoff frequency. And so you see if the input frequency is equal to the cutoff frequency, the phase is negative 45. If f goes to infinity, this is going to saturate at minus 90. And if f is 0, the input frequency, the output phase lag is going to be 0. And so that makes sense. If you put in a DC current, your output is not going to lag by anything. If you put in a very, very slow frequency, right, that capacitor has plenty of time to fill up and empty, But if you put in something that's super, super high frequency, that capacitor can't keep up, and your output is going to lag behind by 90 degrees. But according to this equation, it's not going to lag behind by more than 90. Why doesn't it lag behind more than 90? Honestly, I'm not sure, but that's how the math works out. So this has been a very, very quick crash course on op amps. I did the simple non-inverting amplifier. I showed you the simple inverting, and I encourage you to work this out by hand and make sure you get the same equation. And I also encourage you to go through this and make sure that you get the same equations. So I hope this helped. I hope you enjoyed the video, and I will see you in the next one.